Hi everyone, we are from Team 4 and we will explain to you guys about question 2 for the team assignment 1. This is the question that were given to our group, which is question 2. The Sultan Mahmud Power Plant on the Kenyir River, Terengganu produces electrical power by allowing water from the upper river side of the dam to pass through turbines to the down river side of the dam. The water passing through the dam drops 100 feet. 1.350 times 10 to the power of 5 kilowatt of electricity are produced in a single turbine, with the frictional losses through the dam are 5 joule per kilogram, and the efficiency of the conversion of mechanical energy to electrical energy is assumed to be 100%. First question, A. Draw and label the diagram of the process. As you can see, this is the drawing that our group come out with, which consists of dam, turbine, water inlet and water outlet. There are also several information that we can get from the question. First, 100 feet, which is the distance between point 1 at dam water level and point 2 at water outlet. Turbine efficiency, which is 100%. Frictional losses, 5 joule per kilogram. And lastly, negative 1.35 times 10 to the power of 5 kilowatt of electrical energy produced by a single turbine. The value is negative because the work come out of the system. For the basis of this question, since we don't know the mass flow rate yet, so we need to find the mass flow rate later in part B to make it as our basis. And for the reference state, velocity is 0 at point 1 and Z, which is height or depth, is 0 at point 2.
For part B, what is the flow rate of water in meter cube per second passed through the turbine? Basically, this question asks about volumetric flow rate of water. First, we use the formula of efficiency to find the mechanical energy or work shaft. The efficiency given in the question is 100%. The formula of efficiency is electrical energy divided by mechanical energy times 100%. When we solve the equation, we get the work shaft is equals to negative 1.35 times 10 power 5. Next, we use the general mechanical energy balance, which is delta P over rho plus delta U square over 2 plus G delta Z plus frictional loss is equals to work shaft over mass flow rate. We can assume delta P equals to 0 since the question did not mention about change in pressure. For the velocity, the inlet velocity is equals to 0 because we take point 1 at the surface of the water, while outlet velocity is actually significant, but since the diameter of the pipe is not given, we can assume it to be 0 as well. So delta U is equals to 0. First, and then we find G delta Z. We substitute the value and change the unit to get the answer of negative 299.012 joule per kilogram. Next, we rearrange the equation to find the mass flow rate. Mass flow rate equals to work shaft divided by G delta Z plus frictional loss. We substitute all the value and get mass flow rate equals to 4.59 times 10 power of 5. After that, using formula of density, which is mass divided by volume, we can find the volumetric flow rate of water passed through the turbine equals to 459.16 meter cube per second.
For part C, if the efficiency is not 100%, what happened to the flow rate of water in part B? Substantiates your answer. So, first of all, we have the mechanical energy balance equation. As we already did the assumption in part A, we can just ignore two of these. What we left is just G delta Z plus frictional loss equals to shaft works rate over the mass flow rate. It is equation 1. For equation 2, we have the mass flow rate equals to rho times volume flow rate, which is equations 2. As we know, the equations of the efficiency is equals to work flow rate over the shaft work flow rate. So we can know that actually the shaft work flow rate is equals to work flow rate over efficiency, which is our equation 3. Then we sub equations 2 and 3 into the equation 1. Then we will get this equation. After that, we move the volume flow rate to the left and all the others unknown to the right. So we will get this equation. According the equations above, the efficiency of turbine, which is E, is inversely proportional to the volume flow rate, which means that when the efficiency of the turbine decreases, the volume flow rate of water will increase. To prove that the statement is correct, we assume that the efficiency is less than 100%, which is 0.3. Since that we have the value of the efficiency and the G delta Z, which we get from part A, we have the rho value of the water, and we also have the shaft work flow rate that we get from part A also. We can sub all these values into the equation that we get just now, so we can get the volume flow rate. As the volume flow rate at part B that we get is actually higher than the volume flow rate in part A. Thus, it proves that the volume flow rates of water increases when the efficiency of turbine decreases.
So now let's move on to part D of the question. In another occasion, small steam turbines intended for generating electrical have mechanical outputs of 1.350 times 10 to the power of 5 kilowatt. The steam enters the turbine at a pressure of 10 bar absolute and a temperature of 600 degrees Celsius. The steam leaving the turbine is at 1 atm absolute pressure and having 90% quality. What is the flow rate of steam that has to go into the turbine to get 1.350 times 10 to the power of 5 kilowatt of shaft work out? So basically the question here is asking us to find the flow rate of the steam at the input stream. So first of all, we would have to convert all this information into a visual diagram. So as you can see here, this is our turbine, which consists of one input stream and one output stream. And therefore we have to label all the components of the turbine, including m dot, p1, p2, t1, t2, and even x, which has already been given as 0.9. And also, we must not forget to add the reference state and the basis for this problem. So the reference state here is water at 0.00611 bar and 0.01 degrees Celsius. However, for the basis, we don't have the basis yet, so we have to calculate the flow rate at the input stream to obtain the basis. So now moving on to the next slide. The first step here is to write down the energy balance equation, which is delta H plus delta EP plus delta EK equals to Q dot plus W dot. And after writing down this equation, some components of this equation could be neglected. For example, the delta EP, which is the change in potential energy, could be assumed to be 0 because there is no elevation or height change. And the delta EK, which is the kinetic energy, could be also neglected because there is no velocity present. And also for Q, which is the heat transfer, it is also 0 because there is no heat transfer in this process. And therefore we end up with this equation here, which is del H equals to W dot S. And then when we expand this equation here, we will obtain this equation over here. From that, we have to continue to find H2 and H1 to obtain the value of M, as W dot is also already given. So the first step first, we have to first find out whether this is a saturated steam or it is a superheated steam. So for that, we have to write again the reference date, the same reference date, and then we can refer to table B7 at pressure 10 bar. We can obtain the value of Tsat, which is 179.9 degrees Celsius. As T1 is more than Tsat, thus it is a superheated steam. So now we are going to find the values of H1. So by referring to the table V7 at the pressure 10 bar and temperature 600 degrees Celsius, we are able to obtain the value of H hat 1, which is equals to 3697 kilojoule per kg. And then we can convert the P2, which is 1 atm, into 1.01325 bar to find the value of T2. So based on table B6, at the pressure P equals to 1.01325 bar and the saturated temperature 100 degrees Celsius, we are able to obtain the value of T2, which is 100 degrees Celsius. And also we will be able to obtain the value of the specific enthalpy of water, which is 419.1 kilojoule per kg, and also the specific enthalpy of C, which is 2676 kilojoule per kg. And therefore, by using this equation here, so by substituting all the values that we have into this equation here, we will be able to obtain the value of H2 hat, which is 2450.13 kilojoule per kg. And therefore, the last step is to input all the values of H2 hat and H1 hat into this equation back to obtain the value of m dot, which is 108.29 kg per second. That's all from us. Thank you.